Okay, today we're going to talk about Unit 6, Subunit 8, Kinetic Molecular Theory. And kinetic molecular theory is basically the way or the theory that we use to explain the behavior of a gas. And we have drawn particle diagrams of gases in this little box, but we really didn't discuss what's actually happening in that box in terms of the particles. So that's what we're going to do today. I'm going to be flipping back and forth between this screen and this screen, where we have our major assumptions of the kinetic molecular theory, and we'll go through each one of these 4 major assumptions, but I'm going to draw them on using this particle diagram so you can see what each one of those means. So let's just talk basics. In this diagram, we have these little red dots, and the little red dots are referring to the individual gas particles. So the first thing the kinetic molecular theory says is that these gas particles have no volume. So basically what they want you to believe is that if I took all of these little gas particles and I squished them up so that they were right up next to each other. Let's see, I'll get my pen. And I took the gas particles and I took all of those individual gas particles that are spread out to fill the entire volume of their container, and I took those gas particles and I squished them all up so that they're all in one little corner. I don't know if there's the same number here as here, but you get the idea. If I did that, then the volume of this blob of gas particles would be so small compared to the volume of the entire container. So this is the entire container, and let's say the volume is 100 milliliters. We'll just make that number up. We'll say that this entire gray square had a volume of 100 milliliters, and if the gas was left to its own devices, it would fill the entire 100 milliliters. But if I squished all the actual gas particles down so that they were all up against one another, the volume of that blob of gas particles would be maybe 0.0001 milliliters. So the volume of the actual gas is negligible compared to the volume of the entire container. Okay, so that's what the first assumption of the kinetic molecular theory says to us. It says that gas particles have no volume, that they take up no space. They're talking about the actual, let's get a pen. They're talking about the actual gas particles taking up no space. Now, is that true? Not really, because they do take up some space. It's just really, really small. Sometimes they use the word negligible. Negligible. I hope that's how you spell it, okay? So it's negligible in comparison to the volume of the container that the gas is taking up. So let's go back and let's talk about the fact that the gas particles are not attracting one another. They have no intermolecular forces of attraction. So if I were to go back to this diagram, I would say that if a gas particle, this gas particle and this gas particle got close enough to each other, they would not attract each other at all. There'd be no attractive forces between this gas particle and the other, this one right here, number 1 and number 2. There'd be no attractive forces. Same thing with gas particle number 3 and number 4. They wouldn't attract each other at all, so that they would spread out indefinitely, except for their being held in place by this box. So that's the second postulate, we'll call it a postulate, of the kinetic molecular theory, that they do not have any attraction for one another. The third one is that these particles are randomly and continuously moving within this box. Okay, so each one of these particles, let's get another pen, this particle is moving and it's moving and it's moving. It can go in any direction it wants. That's the random, and it's moving all the time. They never stop. Okay, that's what gives them kinetic energy, right? The energy of motion. That's why gases have temperature, whether they're really low temperatures or really high temperatures. But these guys are constantly moving, and we really don't know what direction those particles are going to be moving in. So that's the third postulate of the kinetic molecular theory. And then finally, our fourth postulate says that when these particles do hit each other, because they will, right? That guy and that guy will hit each other. They do not lose any energy when they hit. Now, if you can imagine, if we had a car, here, let's draw a little car. Okay, so that's the car, that's me in the car. Vroom, vroom. And we draw a car going in the other direction. It's a really bad car. And there's somebody else driving that car, right? We got to give it some wheels. When these two cars hit each other, boom, boom, they're going to exchange energy and they're going to stop. Okay, they're going to exchange energy and they're going to stop. Well, when we have these particles colliding with each other, this one and this one, we're going to pretend that they don't lose any energy. So therefore, if they don't lose any kinetic energy, energy of motion, their temperature will never change. Oh my goodness, how do you spell temperature? That was not it. Oh, hey, come back. I need temper. You would think I wouldn't know how to spell temperature. Temperature. Okay, their temperature doesn't change. Okay, and we know that can't be true, but the kinetic molecular theory makes us assume these things. So there's four things that are being assumed here. One, there's no volume. So they're saying the particles, the actual particles of the gas, have no volume. Number two, they do not attract. Okay, in fact, they do attract each other just a little tiny bit. Number three, they have perfectly random, continuous motion. They're random, continuous motion. That means they never stop. And then finally, that when they do collide with one another, sorry, I was getting interrupted by the dog at the door. So, number four, when they do collide with one another, they do not lose any speed. No loss of energy. Okay, or we can say speed of the molecules because it's the kinetic energy that we're looking at. So if they're not losing kinetic energy, they're not losing temperature. Temperature. It's very hard to write with this thing. Temperature. Okay? So these are the four things we have to assume in order to have what we call a perfect gas. Now, are there any perfect gases in existence? Are there any gases that have no volume, that do not attract each other, that have random, continuous, straight line motion? That means they go on forever and ever and ever, and they never change. And then no loss of energy or speed. Well, this doesn't happen. This only happens in what we would call an ideal gas. Okay, so I'm going to go to the next page so I can show you where the notes on that are. Okay, let's see. Ideal gases. Where did I write that? Here we go. Kinetic molecular theory, right there. Kinetic molecular theory, KMT, is based on a concept or a model of an ideal gas. That means a gas that is perfect. Are there any perfect gases? Perfect gas. Let me make that smaller. Okay, there are no perfect gases. There are no gases that do all four of these things perfectly. Okay, there are two gases that come close to being ideal. They are hydrogen and helium. Now, my time is running out for my screencast. I only get 5 minutes, so I'm going to say goodbye. I hope this helps you with kinetic molecular theory.